Okay, so the recording is live. So let us start. So welcome everyone to today's session of Majorana-Raychaudhuri seminar series. Our first speaker today is Dr. Ido Ben-Dayan from Ariel University, Israel. And the title of his talk is The Improved Null Energy Condition uh, towards, Null Energy Condition. And Dr. Ben-Dayan, we are delighted to have you, and the screen is yours.
Thank you. Thank you very much. It's a pleasure to be here. Let me just a second. Okay, so right. So today I'll discuss the improved null energy condition. It's a quantum energy condition, and I'll describe a published work from 2024, and we're at the final steps of proving the condition, or proving it at least in some cases. And this is done with my student Ayushi Srivastrava, and I expect that it will be published in the next week or 2 weeks at most. So let's see. Please feel free to stop me at any time with questions. I assume the audience is some form of high energy particle cosmology theory people, so I hope the level will be suitable for the audience. So, let's start with some basic things: general relativity and semi-classical gravity. Then I'll describe what is called the quantum focusing conjecture. I will then go on to discuss the improved quantum null energy condition, or INEC for short. And finally, I'll show, at least a proof in some cases of the INEC on the past light cone. So, right, what does the general relativity tells us? Tells us that geometry equals energy, right? The metric, we have the Einstein's equation, and it fixes the left-hand side of the Einstein tensor is determined by the metric of space-time, and this is described by the Einstein tensor. That's the left-hand side of the Einstein field equations, and that equals to all the possible energy sources, radiation, matter, a cosmological constant, whatever, which is on the right-hand side of the Einstein equations. So energy curves space-time, and the space-time is dynamical by Einstein's theory of general relativity. Many times we'll use some fluid approximation. That's very convenient, especially for cosmology. So we assume that the energy momentum tensor is a perfect fluid with a diagonal energy momentum tensor, or maybe a sum of non-interacting or interacting fluids. And then rho is the 0,0 component, the energy density, and then the pressure on the spatial part of the tensor. But the theory of relativity does not tell us what are the energy sources. For each problem at hand, I can write down whatever energy sources that I think are suitable. So we don't have a theory for the allowed energy momentum tensor. Actually, we can use what is called the Singe method, which is we can construct any energy momentum tensor that we want. What do? We simply pick an arbitrary metric, GAB, and solve what is T mu nu using the Einstein's equation. Of course, this is not a very, so mathematically this is all well posed and everything's fine. But right, in nature, we don't have any type of energy sources. We have several known sources, and okay, we believe that probably this is not the whole story, but okay, we would like to think what are plausible energy momentum tensors. So if we consider the fluid approximation, so for instance, if we looked at what we knew around the 60s last century, we knew that there are matter sources, where in the fluid approximation it means that the equation of state is 0. We knew about radiation, so W was 1/3, is 1/3, and then this was very useful for proving various singularity theorems. which I'll discuss a bit more in a couple of slides. By now, we also know that, okay, if in cosmology, right, we expect to have spatial curvature, which is equivalent to W, which is minus 1/3. And all the cases of accelerated expansion, whether it's the cosmological constant or inflation, or maybe it's dark energy. So that means that W, the equation of state parameter, is approximately -1. This already violates most of the energy conditions that people thought about. For example, the strong energy condition or the dominant energy condition. So, but okay, there was one condition where these things do not violate or at most saturate it, and this is what is called the null energy condition. The null energy condition, this is a classical energy condition, and it says that for every future pointing null vector field Ka, the contraction of the energy momentum tensor with this null vector should be positive semi-definite. In the fluid approximation, this is equivalent to requiring that W is greater or equal to -1. So for instance, the cosmological constant exactly saturates this inequality. It has W, which is -1. Okay. And then maybe something which is relatively interesting nowadays is that it seems that maybe the dark energy that we measure now maybe has a varying equation of state, and it seems that at some point in the past, W was even less than -1, which means that even this null energy condition was violated. Now, why is this so important? So this is very relevant for the Raychaudhuri equation, which is crucial for analyzing singularities in general relativity. So let's consider a congruence of geodesics. So there is some infinitesimal cross-section calligraphic A, and here I plotted some, let's say that these are geodesics. So we see that the geodesics evolve and A obviously changes. Since these are null geodesics, we can parameterize them by the affine parameter lambda. And then we can define a classical scalar expansion, usually denoted theta, which is the logarithmic derivative of this infinitesimal cross-section with respect to the affine parameter, as described here. So that measures, right, the expansions of the geodesics. And this brings us to the Raychaudhuri. Yes.
My PhD days, I also happen to have done the same supervisor. My PhD day was various story times I had done during this.
I cannot hear you. Sorry, I couldn't understand what you're saying.
Some issue with the audience. It's okay. Please continue.
Okay. Okay, so here I wrote the Raychaudhuri. The Raychaudhuri equation is more general than what I've written here. It can have also shear and torsion terms. Let's, for simplicity, assume that these shear and torsion terms vanish, and therefore it says that the variation of the expansion scalar with respect to the affine parameter equals something which is the expansion scalar squared. So this is definitely a negative term. And this term, which is a geometric term. This is true for all metric theories of gravity. If I assume Einstein's equations and not some generalized gravity theory, then I can use Einstein's equation, and then I get here the energy momentum tensor. Okay. So, right, so here is where energy conditions are useful. So if we assume that the null energy condition holds, we know that this derivative of theta is negative semi-definite. This inequality we can easily solve, given some initial condition theta naught. And if theta naught is negative originally, so if originally these geodesics are contracting, we know that what is called a caustic is formed at finite lambda. And this Raychaudhuri equation is the basis of singularity theorems. There is more mathematical work to do, but that's a very major and important step. The fact that, okay, we try to solve the Raychaudhuri equation, and we see that at finite affine parameter, and for time-like geodesics, we get it at finite proper time, a caustic forms. Okay, so I think most, if not all, of the singularity theorems will not or do not hold, or we don't know whether they hold or not without this assumption. So it's a very crucial assumption. Now, this has been very useful. We found this way that we prove that there is a black hole singularity, Big Bang singularity. The area theorem of black holes is based on that classically the area can only grow. So all of these are very nice mathematical results. The problem is that they're useless in the real world. Why? Because the real world is governed by quantum fields, and quantum fields violate the null energy condition. It's a very generic property of a field theory, of quantum field theories, that there are states that violate the null energy condition. And therefore, of course, in the approximation where quantum effects go to zero, et cetera, of course that these results hold, but right, this is a very unsatisfactory situation. And we would like to be able to have these theorems at least in the context of semi-classical gravity. So at least when we allow quantum corrections to the energy momentum tensor. So this is under the name of semi-classical gravity. So let's consider a classical background space-time, and on top of that, quantum fields. Quantum fields can perturb space-time in a self-consistent manner. So I have some background metric, and I calculate corrections due to quantum fields that are that exists over the space-time. And okay, it corrects the metrics slightly, but it doesn't, you know, the back reaction on the metric is not so large that this analysis is not self-consistent. This is what we do when we calculate the power spectrum in inflation, and when we calculate perturbations of black holes and gravitational waves. So this is a very good framework. In principle, when we discuss semi-classical gravity, we talk about that we can calculate all. Yes. Hello. We can calculate the corrections to all orders in H bar and to first order in G. Now, from semi-classical gravity, we're able to calculate the generalized second law of thermodynamics by Bekenstein. We have Hawking radiation. This is based on a semi-classical calculation. Cosmology, inflation, theory of large-scale structure, all of this is based exactly on semi-classical gravity, i.e. quantum field theory on a curved classical background. Now, a crucial quantity in this analysis is the Bekenstein-Hawking entropy. The Bekenstein-Hawking entropy, as you can see, it's called the generalized entropy, and this includes the area term of a black hole, and the matter entropy, or by now we'll call it the entanglement or von Neumann entropy of quantum fields on one side of the cross-sectional area. Okay, notice that all fundamental constants of nature appear in this formula. So this is a very important fundamental formula. A is the area of the black hole. And from here, we learn that black hole are thermodynamical objects. It has they have entropy, they have temperature, they radiate away and disappear, which causes what is called the black hole information paradox. And another nice thing is that the generalized entropy is finite, unlike the entanglement entropy. So you can absorb the divergence of the entanglement entropy into a renormalization of the Newton's constant, and that's why the generalized entropy is finite. So what are we going to do? We're going to do the following. Wherever we have area in the classical GR theorems, we're now going to try to, instead of area, write down the generalized entropy there. Okay, this is not suggested by me. I think the main person who started with this idea is Rafael Busso from Berkeley. And of course, a lot of other people did this exercise as well. And this way, what you have is that you can try to now write things with respect to generalized entropy instead of area, and try to, again, prove singularity theorems, generalized laws. For example, they managed to derive a generalized law for cosmology. try to advance in how to solve the information paradox, etc., etc. So again, the idea is very simple. Wherever you have area, now here this is calligraphic A, this is a cross-sectional small area, infinitesimal area. You replace it by 4gh bar times the generalized entropy. So here's the, for instance, the setup. So I have a Cauchy surface, a capital sigma, and here I have a cut of this hypersurface sigma. A is the area of this cut, and N is a null hypersurface that I erect from this little sigma. And this is a sideways version of it. Okay, and then these are geodesics that are parameterized by lambda. Okay, so once we have done that, let me move this. So right here we have some area ball, a ball B, and I have the transverse coordinates y, and I have the null geodesics with vectors k, and I deform the surface by some function. Okay. And then I can define the quantum expansion. Either I do it via functional derivatives this way, where h is the induced matrix, v is this shape function, and therefore this is a shape derivative. Or if I stick to the original notation, then this quantum expansion theta is the classical expansion plus a correction, which is a quantum correction, of course. Now, what does this mean? So this helps us a lot because this allows us to define quantum extremal surface where capital theta, the quantum expansion, vanishes. This is what is crucial in what is called the formation of islands, and this allows us to calculate the black hole evaporation in a unitary matter, and yeah, and this is how we people have reproduced the page curve, which is a unitary evaporation of a black hole. Okay, so this idea of a generalized entropy and quantum expansion is very useful. Okay, so since we know that there is the Raychaudhuri equation, and we know that singularity theorems are based on theta prime less than 0, less than or equal to 0, let's try to do the same thing with the quantum expansion. And this is what is called the quantum focusing conjecture. So the quantum focusing conjecture is a conjecture, it's not proven, which says that the derivative of the quantum expansion with respect to the affine parameter is negative semi-definite. Okay, this is a crucial point that we have, that when we try to calculate the variation of the quantum scalar expansion, we know that it's negative semi-definite. So this is a generalization of some results of the classical Raychaudhuri equation, but it's a conjecture. Now, from this conjecture, now you can derive many results. You can derive the entropy bounds, you can derive the generalized second law, and finally, you can derive what is called the quantum null energy condition. So let's look at the derivation because we will use it for our energy condition. So okay, so I simply write what is the quantum expansion, which is the scalar one plus derivatives of the entropy. I use the conjecture to say that all of this is less than 0. So you see that I can reshuffle the terms, and I basically get that this quantum focusing conjecture is basically an energy condition. You see that T mu nu has to be greater than something, but in the presence of gravity. So now I can consider various limits. So if I take the limit of h bar goes to 0, I get the classical null energy condition. This is expected. If I consider a different limit, let's consider the limit where the classical expansion vanishes, then I get what is called the quantum null energy condition. You see that I get that now this contraction of T mu nu is not greater or equal to 0, which is this case, but greater or equal to h bar over 2 pi a s double prime. Now, s double prime can be negative, it can be positive. So this is this condition is a weaker condition. I can find the example where the classical condition doesn't hold and this condition does hold. And this is quantum condition. This takes into account quantum field theory. S double prime is in principle calculated for quantum field theories. Another important point is that G does not appear in the calculation. So I started from semi-classical gravity, and at the end of the day, I got a result that is independent of gravity. Okay, so I got a result that for field theory, where no matter what gravity theory is realized in our world, I still have a result for field theory, and I got it in 2 lines. Now, can you get this result from field theory? So you can, and this is the proof. The people have proved the quantum null energy condition. But all these proofs are much, much longer than these 2 lines. These proofs are 70 pages proof with long calculations and various limitations. So you see that this idea of starting from semi-classical gravity and then trying to derive results in quantum field theory is a very strong tool. Okay, so this is the QNEC, and it has been proven for field theories. But what was the limiting factor? The factor that theta vanishes. Okay, so right, it was all based on the limit where theta, the classical expansion, goes to 0. Okay, but as I said, the QFC is a conjecture. Maybe it's wrong. So Arvin Shahbazi Moradam in 2023 suggested what is called the restricted quantum focusing conjecture, and actually he managed to prove it in certain cases. And this says that capital theta prime is not negative semi-definite everywhere, but at points that the quantum expansion vanishes, then its derivative is negative semi-definite. Okay, so this is a more restricted version. One can check, and it turns out that all the nice results that we had before still hold even in this restricted version, so it's very nice. But this also led us to think, okay, let's consider this limit of what happens when capital theta vanishes. So we can plug this into the quantum focusing conjecture, and then we get, this is in 4 dimensions, we get a modified energy condition. So now we get an improved quantum null energy condition. Why is it improved? Because I have on top of this second derivative here, I have this additional term. This additional term is non-zero if theta is non-zero. And it can be a stronger condition. So if theta is prime, if minus theta is prime is positive, then it's a stronger condition than the QNIC, or otherwise it holds trivially, right? Because the QNIC holds and proven, so if this thing is negative, then okay, this trivially holds. So we have a stronger condition, which is again a field theory condition. It's independent of G. Questions so far? Because yeah, I want to be sure that people understand what I'm discussing. No questions. Okay. Okay. Of course, this condition can be written in any dimension, as can be seen here. So I can generalize it to any dimension. And we have some evidence that this condition holds, which is, and this has been analyzed already several years ago. So if we consider the vacuum, so this T mu nu vanishes, and we consider spheres such that theta is exactly 2 over r, then we have this inequality has been proven. Okay, so for vacuum, so we have further evidence that this condition is correct in a specific case of a vacuum and spheres with radius r. What are the implications of the INEC? What are the possible interpretations? One is that it's true, and okay, since we'll show some proof of it, so this is probably the correct result. But okay, maybe it's not true, and then the QFC is only a perturbative statement. And okay, there are other possibilities. I don't want to go into them right now. So Okay, so let's try to think of let's try to prove this energy condition. So we have to consider curved surfaces and expand S in powers of the surface and differentiate it and try to prove the condition. So currently, the most efficient way to do these things is if we have a modular Hamiltonian. If we have the modular Hamiltonian, then the modular Hamiltonian is related to what is called the relative entropy and the entanglement entropy in this way. And therefore, if we have a modular Hamiltonian, then we can differentiate it and try to plug it into the INEC and see if it holds or not. The problem is that usually the modular Hamiltonian is something very complicated and non-local, and we don't have a functional form of it. But there are specific cases where we do. Here is one of them. This is the modular Hamiltonian on the null plane, and it's very nice. It's an integral exactly over what we want, the energy momentum tensor. However, there is a problem, which is that I will tell you in advance. There is a problem that this is the modular Hamiltonian on the null plane. On the null plane, we're back in the case, it's a very special case, and this special case is exactly the case where, again, theta equals 0, and it won't be useful. But let's show how from here we prove the QNEC, which is because this is exactly the technique that we'll use to prove the INEC. So you see, we differentiate the modular Hamiltonian twice, and we get 2 pi t equals this thing, S double prime plus the relative entropy double prime. The relative entropy is measuring the distance between two states, where rho is a density matrix, and then log rho is the density matrix of that state minus another state sigma. And it's a non-negative property. It's a monotonic property. And in this case of the modular Hamiltonian from the previous slides, it's guaranteed because of the convex property of the relative entropy, the second derivative is positive, and that's how you prove the QNEC. You can do a conformal mapping, map it to some QFC, to some conformal field theory. And then when you do a conformal mapping, you get anomalous terms. So that's why it's no longer T and S, but T bar and S bar, which include the anomaly subtraction. But here you already see, you get what is called the conformal QNEC or holographic QNEC. And you see that here for the first time, I have an energy condition that includes expansions of geodesics. I will drop the bars from now on, but remember that whatever I do now, it will be with, if I use conformal mapping, I'm talking about the anomaly subtracted quantities. Okay, so let's try to think of some other example, which is not the null plane. So it turns out that I can map the null plane into the past light cone. In the past light cone, I am able to write the modular Hamiltonian in this way. So infinity of the null plane is mapped to the apex, and the arbitrary cut that I had on the null plane is mapped to this cut here. So again, I have a simple expression for the modular Hamiltonian. Here, right, here theta is not 0. At any point here, I have a sphere which has an expansion. And the spheres vary with radius according to gamma. So it's not everywhere it's the same same radius. Okay. So here is the conformal mapping. I map the cut gamma, and I have here an affine parameter S, and alpha is a positive. That will be my derivative with respect to S, and it's a positive thing. The expansion is the derivative of the logarithm of the determinant of the induced metric, and can be positive or negative. On the past light cone here, gamma dot is negative, so theta is negative. And when I map the properties of the relative entropy, so I get that the first derivative is positive, and I get that the second derivative is not always positive, but that the sum of derivatives is positive. So now everything is in place. We can differentiate the modular Hamiltonian twice. We can substitute that into the INEC and see whether whether I can prove the INEC or disprove it, or find some sufficient conditions or anything. So here we substitute. So we took all these results from this, the properties of the modular Hamiltonian, theta, gamma, the relative the derivatives, etc., etc., and we substitute it into the INEC. So let's see what we have here. We have exactly all these terms, these first two terms here and this term here is exactly the INEC. The INEC holds if this is greater or equal to this. Okay, and now I have here the following terms. So minus d minus 1 over gamma times this thing. This is exactly the first derivative of the entropy, minus this combination of derivatives of the relative entropy, which we just said that it's positive. So basically the INEC holds if, so you see I have here a minus sign and here a minus sign. So the INEC holds if all of this is positive. Okay, so basically the INEC holds if the first derivative of the entropy is greater or equal to something which is negative. Now, right, so as I said, the only interesting case is, I think I wrote it here somewhere. Right, we care about only if minus theta is prime is positive. If not, then the INEC trivially holds. So, right, so we're saying that so what we got from this inequality is that the first derivative of the entropy is greater than something which is negative. Since the only interesting case is when it is positive, it means that the INEC holds. So we have a proof of the INEC. So when theta s prime is positive, this is trivial. When theta s prime is negative, then we reach this situation, and we show, since this by construction is much greater than this, then it means that the INEC holds. If you want, you can write it in terms of a smeared energy condition. Okay, I can translate this condition to a condition on this integral from the apex of the cone to the cut of the energy momentum tensor. And it tells me again that the energy momentum tensor has to be greater than some combination of derivatives of the relative entropy. It's not exactly like here, because here I have 2 and here I have 1. But so that's why I cannot say that this is greater or equal to 0. Okay, but what we have is that we wrote down the modular Hamiltonian on the past slide. Hello? Hello?
I think it's a problem with the audience, issue with the audience. It's okay. Please continue.
To continue?
Yes.
Okay. Okay, so we have proved the INEC, at least in this case of the past light cone. So the INEC holds, and you can view it as, again, you can view it the way we wrote it, or you can look at it as some integral condition on the energy momentum tensor. So let's think of further implications of this result. And so this was proof of INEC. Now let's think of further implications. And when I say further implications, I say back towards the semi-classical gravity. So one thing is that if the INEC holds, we can rewrite it. It basically means that the second derivative of the generalized entropy is negative. So it means that this the quantum extremal surface is not extremal, but actually a maximal surface, okay? Because S prime gen is 0, right? And then S double prime gen is negative. So this is a maximal surface and not an extremal surface. Now let's consider the other and the opposite approach. Since we have proven the QNEC and the INEC to a certain extent, let's think of them as the basic quantities and try to, from them, to understand what will be a more general or a more correct quantum focusing conjecture. Okay, so here's, for instance, if I say that the QNIC is fundamental and always holds, I actually get a modified QFC. This is in 4 dimensions, which is very nice, right? It looks a lot like the quantum Raychaudhuri equation. And in general dimension, I have this additional term here. Okay. So this is if the QNIC is always correct, and I want to generalize it back to semi-classical gravity, then I get a modified QFC, which is written down here. I can do a similar exercise for the INEC, and I get again this capital theta squared term and another term which is proportional to theta. So the restricted QFC works and everything works. So in both cases, I get something which looks like a quantum Raychaudhuri inequality. And I get that all the terms here, both here and in the previous slide, you see that all terms are second order in quantum corrections. All terms include h squared and even gh squared. So this is nice because it means that, okay, you know, it seems that we're getting some self-consistent quantum expansion and the quantum Raychaudhuri equation. Yes, so let me summarize. So from semi-classical gravity, we can derive field theory consequences in a simple manner. That's very nice. We got a new energy condition. These energy conditions are not based on familiarity, unlike the energy conditions that people used in the 60s. Here, these conditions have been proven from first principles. We're gonna publish the proof in the next couple of weeks, I hope. And we're now also thinking about cosmological implications of these conditions. So thank you.
Okay, thank you for the talk. So if anybody has any question, please unmute yourself and ask. Okay, if there is no any other question, let us thank the speaker. Thank you for your nice talk.
Thank you.
Thank you. Okay. Our next speaker is Professor Kaushik Bhattacharya from IIT Kanpur. Can you please share your screen?
Yeah.